In this session, I'll be talking about IEEE 30,000 foot level reporting for attribute data. At the end of this module, you'll be able to assess predictability and capability statement with attribute data. You'll be able to also apply these techniques to infrequent event occurrences of attribute data, for example, safety events. We'll also be discussing how to show and quantify the magnitudes of reported improvements, and then also where we should focus improvement interests when we're dealing with 30,000 foot level attribute charts. So again, there's two steps for the overall 30,000 foot level process. Step one is assessing the predictability of the metric. If it is predictable, then you would determine a process capability of performance value. Now, it's easier to do this with attribute data than continuous because we don't have a probability plot associated with it, with this form of reporting. So before we were with continuous data, we were up in 3.2.1. Now we're down to 3.2.13. where that's dealing with the attribute various scenarios. So this chart, again, this decision tree is to address process stability, where this one is to make a statement of how the process is performing if it is stable. So several things we're going to be talking about here is, one is a non-conformance rate for a time series of events. We would use the EPRS attribute or option attribute. We'd also talk about infrequent failures, quantify improvements, and then also look at where we can focus our improvement efforts. So this is where we're going to start, where we got data, and then now we're trying to determine if or create a 30,000 foot level metric for tracking failure rates. So let's consider in this example, we got web orders, and there's a bunch of them that comes in each day. And if the transaction, if it doesn't go through the system first time through, then it's recorded as a failure. So first off, is the process predictable? And that's what we're going to assess first. So let's load up the data set as shown here. And then what we'll do is, well, you first got to calculate the failure rate if it's not already there. The way you do that in Minitab is go calculator, and then you get this screen here, and then you can create a new column, store results in a variable, and that's your new column, and then you can get your expression in the expression window. So for this particular analysis, we go to IEEE attribute. We'd enter the values shown on the yellow box on the left-hand side, and voila, you get this particular 30,000 foot level chart. So we're saying we estimate the performance to be about 0.02. So let's look at another situation. Produce a cardboard container. They inspect about leakage. Let's hold up this data set. For those that are in the transactional world, this could be, instead of an orange juice container, it could be a transaction that went through a process. So the form either fails or not, fails for one or more reasons. So let's open up the EPRS add-in. For this data set, we'd enter the items that we have showing in the yellow box on the left-hand side. So for this predictive data set, this is what we get as a response. We got about 23% non-conformance. So other things that, so this sort of reporting is nice. However, you do have some challenges with it. It's not bounded by physical constraints. So for example, an eye chart might be below 0. That's what occurred in the previous analysis. You can see that we had below 0 point. So what you can do is you can go in and look about, consider taking a transformation. One thing you can do, go into graph, control towards Box-Cox transformation, and then since it seems like it has a minimum point at 0 value, and the log normal distribution is equivalent of a Box-Cox lambda of 0, then we say it looks like a log normal transformation works quite well. Now in volume 3, I do show various shapes that log normal distributions can have for those that are people that have that kind of interest. For this particular situation, a log normal distribution does make physical sense. So I think that's really one important thing to consider whenever you're doing transformations. So now if we open up these noted values here, these noted values for the attribute scenario, then we get a Box-Cox transformation shown in lambda equals 0 at the top there as a header, and we got values at the bottom that estimated performance is in real units, even though the y-axis on the plot is in transformed values. We notice how it's got a natural scatter to it, so that makes us a little feel better. In this particular case, the non-transformed did not indicate any special cause signals, but it could have. So let's now move on to infrequent failures. So this often is analyzed using like a C chart. Technically, it's count data, maybe how many counts, how many failures you had in last month, or very monthly. But it's really kind of a chart that's not very exciting when you're looking at it here. So what I do is I prefer to look at the time between failures. So in this case, you may have the data set looks a little differently, but it's going to be a lot more valuable to you. So let's load up this data set here. We notice the worksheet. We've got also the number of incidents by month, and we've got, for various failure numbers, we've got the time since the last failure. C4 and 5 are recovered time between the failure data. So from this figure 10.1, page 229 in volume 3, we would create a C chart value that looks like this. Well, that's not very exciting. A lot of months have 0, which is not bad, but it doesn't give us much insight. Whereas instead, I'd prefer to do a situation that would look like this and test for predictability, and then we look at a transformed value. And we look at it also, well, we look at it as a time between value, so it becomes a continuous response. That's where we're at. It's not an attribute response any longer. It's continuous because now we're looking at the time between events. So if we follow this logic, then we run into no subgroups. So now this is what we have time between failures. So we estimate the median is 84 days or whatever, and 80% of the events between 50 and 117. It's common cause variability. Now the nice thing about plotting this chart out is that all of a sudden you make a real big gain. Let's say you moved up to 140 or 150 time between events, then you say, hey, we made an improvement, or we believe we did. So you can get quicker feedback with this sort of metric tracking. Predictable process, and like I said, 84 days between events, and 50 to 117 days when 80% of the events occur. In other words, 4 out of 5 times it's going to be within that range. So let's now look at quantifying improvements. So the metric is report daily percent yield. So this is the data set that we're dealing with. So load that data set up, go into EPRS attribute, put those data points in there. You notice that the plots on the left-hand side, it indicates that they're higher. It looks like we have a shift. So investigating 16 was a new process sequence implemented to account for the new contract requirements. They didn't expect it to affect quality, so it looks like we might need to go in and look at individual chart with staging. So if you go in an IEE attribute, enter these values that are shown there, then we can see how we're performing. So now it's an estimated performance rate of 5.0%, about 5% non-conformance. So where do you go next? Well, let's say we wanted to improve this. One thing you could look at is the type of defects that you have. And so Pareto charts can be useful for helping you identify that. So we do have a Pareto chart function in the EPRS. So if you go EPRS run IEE Pareto chart, so type 3 is the most frequent type of failure that occurs. Question is, should this be focused on a project? Maybe, but let's look at it from another point of view. If we were going to look at the cost of doing nothing differently, we get a different type that's financially impacting us more. So you can weigh both of those Pareto charts to give you some insight to where you should focus your improvement efforts initially. So basic conclusion, the process has been predictable during the current state. Capability is about 5%. It's going to make that level. We expect to be at that level until change has been made. The impact of the defect rate is driven by type 4, which is generally 45% of the cost of doing nothing differently. So again, this is going to remain at this level until we do something different. That's assuming, obviously, that nothing on the other side of the coin turned against us. So we could have had a change in the quality of our supplied components, and therefore we could have had our rates have gone worse. Well, that would be then a signal we need to do something differently. So the 30,000 foot level charts can also be used as a control mechanism. So it's something you keep your eye on. If it gets worse, then we need to take immediate action. So these are things we covered: how to assess predictability and capability with attribute data, how to assess predictability and capability with infrequent events, situations, how to show and quantify the magnitude of reported attribute measurement improvement, how to focus improvement efforts when the 30,000 foot level chart is unsatisfactory. The third bullet I want to just emphasize again, I think that's so important that you want to be able to demonstrate how much you improve the metric that project you're working on is to be improving.